everybody. I was going to say good morning, but I don't know what time zone everybody's in, so that may not be appropriate for everybody. Welcome. Looks like we had a few more folks coming on, so we'll let them keep going on. But we'll go ahead and get started here, just because we got a lot of content to cover, and we want to make sure we get everything covered. So first, you're getting muted on entry. We're just going to keep folks muted just to make it easier to hear and to understand folks. You can go ahead and keep your videos off. Just keep our bandwidth going. We'll have the presenters have their video on, but if things aren't going, if you're having a hard time, you could send us a message and we could turn off their video so that we could free up bandwidth so you could see the screen and what's going on. So just a couple housekeeping pieces. One, we are going to record this video because we want to be able to use it for other things or other people. So just a heads up that that's happening. In terms of questions, we're going to go ahead and manage questions via the chat. So if you have a question, you go ahead and throw it into the chat window just to help keep things moving well. I'll interrupt. I'm going to be the only one who interrupts our presenters. Otherwise, we'll either answer in the chat if it makes sense to do that, or I'll get your question in there. But go ahead and throw them in the chat either to me if you just want me to see them, or you're welcome to throw them with everybody. That tends to work pretty well too. And then just in terms of what we're covering today, so I had the bulleted outline as the invite. The piece that we're not covering today is setting up and installing ReEDS, so like the GitHub stuff, making sure you have Python and R working. The README in the GitHub repo should cover that material. So go ahead and just follow the README in the GitHub repo if you're struggling with it beyond that, or something's not working. We have seen some weird stuff happen. So if there's something weird going on, you're certainly welcome to contact us to help work through things. And our group's not a tech support group, but we are interested in making sure people could use ReEDS. And so if there's something we could do, or we need to update the README to reflect an instance that we haven't run across yet, we're very happy to do that because we'd like folks to be able to use the model if they want to. Okay, so that's everything that I wanted to cover. So again, if you have questions, throw them in the chat box, and then we'll go from there. So Max is going to kick us off. So Max, let me make you a presenter again here. Okay, I can't hear you, Max.
My artwork isn't.
Okay, now it's coming through.
You can?
Yep.
Oh.
Your video is kind of choppy and slow though, so I'm gonna turn off your video and just let you show your screen so we don't eat up too much bandwidth there, if that's okay.
Cool. We good?
Yep.
Awesome. Thank you, Wesley. So I'm going to start with just a few slides here to cover just a very general background of ReEDS and some of the most important items you need to know when you're thinking about modifying the model or running the model, those sorts of things. So just in general, ReEDS is NREL's flagship electricity capacity expansion model. It's been around since 2003, focusing more on the details of the model. The objective is to minimize costs of operation and investment, and we'll walk through a very simplified version of the objective function in a little bit. There is kind of the special sauce for ReEDS is this detailed characterization of variable renewable capacity. It is the regional energy deployment system, and so we have this high spatial resolution. There are 205 balancing areas, 134 for the US, 20 for Canada, and 51 for Mexico. In the open access version, it's just the US version, so you can think of this as 134 balancing areas and 356 wind and CSP resource regions. We have the major constraints. I'm not going to go through all of them. The main thing is that these we could talk about more if anybody's interested, or if you have questions on these, reach out. I'm not going to walk through the actual math for these, but I do have some slides drafted up that are under review that would help people at least get knowledge of how these constraints work and how we conceptualize these. So in 2017, Kelly Urich, David Beelan, and I rewrote ReEDS from scratch. And in doing so, we added a bunch of different features. These are the sorts of things that we enhanced on the model. So before we had to solve biannually, and now we're going user-specified years. And so I can go into a CSV file and say, I want to solve 2010, 2015, 2020, or 2010, 2011, 2012, et cetera. We do have this user-specified technology resolution, which I'll go through it very, very lightly later on, and explicit tracking of model plan vintages, meaning I can, before in ReEDS, there's kind of this amorphous blob of capacity available to people or to the model. And in this way, we can track, this plant was built, and if we wanted to, we could say this plant was built in 1976, and it exists in 2020, and it has this amount of capacity, whereas before there was just kind of this, aggregated set of plants. We have user-specified time horizons, meaning we have a myopic view, a sliding window, or a full intertemporal solve, meaning in the sequential case or myopic case, you solve a year assuming those conditions are going to last for the next 20 years. In the sliding window case, you can see maybe 5 years in the future, and then you assume that last year is going to last for 20 years, and then you move forward 1 year, and then you solve that same sliding window with the same assumptions after fixing the years behind you. And then the full intertemporal case is a representation with full foresight. So if I'm sitting in 2010, I can see exactly what's going to happen in 2050. We've added in this capability of endogenous retirements and refurbishments, and in the 2020 version, we'll be refining that a little bit, and then we significantly shorten code length. And I put this iteration with detailed residential demand side. I put an asterisk on this. So when we were building the model, Dave Beelan mainly focused on building out the demand side. And in that, we have, I think it's 12 income classes at the 134 resource regions with, 73 different uses for electricity, all these sorts of things. The asterisk is there because we haven't really, had the opportunity to maintain that. And if anybody's interested, reach out, it'd make a good dissertation topic, those sorts of things. And it's not that much work to get it going. And then finally, we did make it publicly available, which is why we're doing this public instructional series now. If we're thinking about, if you remember, I said there's 134 balancing areas and 356 wind and CSP resource regions. If we're thinking about how that looks on a map, I can look at, I use North Dakota for a lot of examples, and here's P37. So this green area here is the balancing area. Within that balancing area, you have, I'm looking closely now, these 99, 102, and 103 resource regions where you can build wind and CSP capacity. So I can build capacity essentially at these subregions, and that gets aggregated up in the model for generation at this P37 level. The same for Colorado. I have two balancing areas, this beige color and this green color, but then inside those balancing areas, I can have these wind and CSP resource regions where capacity is built, and each one of those resource regions has its unique capacity factor and characteristics, as well as the cost to connect that capacity to the grid. It's just good to keep this in mind when you're thinking about the ReEDS model. So when we're getting started, just a very, very, we're going to jump right in now. I always start with cases.csv or cases_x.csv. I put X in there. You could call it X could be test, Max Brown, Wesley Cole, those sorts of things. But these are the scenarios that were going to be run when I call the model. This is where I start when I start producing cases, those sorts of things. It's a way for me to enter in options or global arguments for these different cases. Now, I always, after processing the cases.csv file, I'll go to Runbatch.py. I'll say Python Runbatch.py on my command prompt or my terminal, and that processes the arguments that are provided in that cases.csv. Now, for each of those cases, and I'll go over this briefly very shortly, but the logic is that I'll set up the cases in cases.csv. I'll call Python Runbatch.py, and then what Python Runbatch.py is going to do, it's going to, for each of those cases in the columns of the cases.csv file, it's going to copy over all the necessary files. It's going to make a directory in this run/case folder, and it's going to copy over all the necessary files. There's case-specific inputs. It's going to create a directory that is cases, inputs case, so runs case, input case is where all my input files are going to be stored. There are several input processing scripts that are used, and all the inputs that are used for a specific case are stored in this folder. it's going to create, the next step it'll do is it'll create this call underscore case.bat or .sh file. And this, what this is going to do, it's going to contain the commands that will run your case. And so I'll cover that briefly in a little bit, but the main thing is it's going to create a directory. Within that directory, it's going to create the inputs case file. It's going to write this set of instructions to a batch or a shell file. And then the command to run that batch or shell file is going to be entered into a threaded queue. Now, a threaded queue, this is done within Python, but what that is you can think of the DMV, and a case essentially will take a number and it'll wait in line until it's called, and then it's going to start. And so we'll go over, how those lines are set up and how many, cases can enter each of the lines, those sorts of things. But for now, it's important to know Runbatch.py will take each case, create a directory for that case, put all the inputs in inputs case. It'll create this set of instructions in the batch or shell file, and then it's going to enter that batch or shell file into this threaded queue. Now, the call underscore case.bat or shell file issues commands to run the case. Within this call.batch or .shell file, the first command is to create model.gams plus a whole huge string of global arguments. There's several lines of global arguments that are passed in here that are processed from that cases.csv file. Now, what createmodel.gams does, and I'll walk through this, it's literally 5 lines of code within createmodel.gams, and what it's doing is it includes, you can notice this $includes, I did this intentionally because what GAMS does when it does the $include sign is it essentially appends code directly where that include command is. And so all you'll see in createmodel.gams is include awrite data.gams, include b inputs, include c supply model, etc. So when it does this, it's a very short file, but it's compiling or combining several different files, which are very, some of them are very long. And what these files do is dependent upon which file it is. And so awrite data will call all the data processing commands to Python or R. So in awrite data, there's, I think, 7 or 8 different calls to Python or to R, or R script more appropriately, that take the arguments that are passed to createmodel.gams and processes inputs such that they follow the logic that you hope for your case. We'll cover that briefly. B inputs is the longest of all of the GAMS files, and what this does is it loads in the CSVs and translates that data to GAMS, meaning I need a way to say, here is my unit database. How do I want that to be represented within the model? And I can process the data immediately, but then there are some things I have to do to get GAMS to see that as a viable parameter that I can use in the model. C supply model is where all of our variables and our constraints are defined. So I'll declare all the variables in C supply model, and I'll define all the constraints there. All the logic for the entire model is there. C supply objective is defining the objective function. We do that separately just because it gets to be, probably about 100 lines in the open access version. And then D solve prep is where we prepare the case for the path to the solve. And this really depends on, you'll see in there's different arguments for time type. So time type is a global argument that we've defined in cases.csv. And what this does is it says, oh, well, you're running the myopic case. I'm going to set up everything for your myopic case. Or, oh, you're running the intertemporal case. I'm going to, set up my present value factors for the intertemporal case. It just gets everything ready for the specific type of solve you're seeking to do. What happens at the end of this, so createmodel.gams will include each of these 5 files. And at the end, it's going to create what I call a goo file or a G00 file. More appropriately, this is a GAMS restart file. And what a restart file does is it's essentially GAMS way of saying, oh, you ran all this code. I'm going to store all of that information in there. And any commands you use after that, when referencing this file, are essentially appended to the end of that line. So if I ran, 1,000 lines of code, and I restarted from that, if I save that and I restarted from that, I can restart from that file, and essentially my 1,000th and first line of code would be directly from that execution. The other thing it does, in inputs.case, it'll do a GDX, it'll do an execute unload statement, which in GAMS is essentially saying, let's dump all of this data to a GDX file, which is the GAMS data exchange format. But it's GAMS native data resolution, or data format. And this just contains everything that's going into your case. At the end of solve prep, all we're doing, we do some adjustments for capacity, credit, and curtailment. But for the most part, all of the data that's going to be used in your case is prepared by the end of solve prep. And so we dump it all to a GDX file, which is useful when you want to compare across cases the different inputs that were used and maybe the changes that you've made between, different commits to the repo, those sorts of things. Next steps, so after we have this G00 or restart file or goo file, all in the same, we restart from that, but the next steps that occur in the model depend on the case's temporal settings, meaning if I run the myopic case that I mentioned before versus the intertemporal case, the instructions that are sent to the command prompt are much different. And so I'll cover that briefly in the next couple slides. But in general, you just need to think of this as iterating between solve a certain set of years, whether it's 1 year or 10 years or 20 years, and then running our capacity, credit, and curtailment calculations. So these are nonlinear calculations that are done outside of the model, and then we use the information gathered from those calculations to plug back into the model. And then finally, we have the reporting and output for bokeh, which will be covered later in this training session. So in general, if I create model.gams, that'll give me a restart file, and then after that, it'll go into the solve routines and then reporting. Okay? So when I think about these solve routines, we have the sequential case on top, and so that restart file is what this ellipses is supposed to represent. And what happens from that restart file, which has all the data and everything ready for me to solve this case, I solve 2010, I translate the ReEDS outputs for ReFlow. I run ReFlow. ReFlow is our name for the capacity, credit, and curtailment calculations. So essentially, I solve 2010. I do some translation. I run the capacity, credit, and curtailment solutions, and then I translate the ReFlow outputs for ReEDS. Now I solve 2012, and I'll do the same sorts of things. So I'll run through ReFlow, plug those values into 2014, and so on. In the intertemporal case, I can take that same restart file and I can solve all years at once, and then I do these the capacity, credit, and curtailment calculations in parallel. And this will be important for when we actually demonstrate the running of the cases, but it's just important to know that I do the same option, so I solve all my years, and then I parallelize all of these operations for ReFlow, and then I merge and translate those ReFlow outputs, and I plug it back in for the next iteration. What we're hoping to do here, what happens is this will iterate, and there's no real test for convergence on these cases. I've thought of a bunch of them. If you're interested in trying those, I'm happy to discuss those. But for the main point, it's going to solve all years, parallelize all of the capacity, credit, and curtailment operations, merge those outputs, and plug it back in to solve all years again, and continue on, not ad infinitum, but for several iterations. I typically recommend about 5 iterations for the intertemporal case, but that's subjective for the sort of case that you're running. If I run a very intense case where I have a lot of things changing over time, you might need more iterations. Now, I mentioned we would discuss the objective function very quickly. So Z is my objective function value, and I'm seeking to minimize this value. And what this is doing is, in the sum of years for modeled years, I'm taking the discount rate for investment times the cost of investment times investment. So this is my investment cost plus the discount rate related to operations times the cost of generation times generation plus the fixed cost for capacity times capacity. Now, this is very simple, but it becomes very powerful because I can maintain the same objective function whether I'm doing the myopic case, the intertemporal case, or anything in between, but all I have to do is change these delta symbols. So I can change, delta I being either the discount factor or the present value factor for investment is different than the discount factor or the present value factor for operations, meaning if I can explain that more, but in a very simple sense, in the myopic case, the present value factor for operations is going to essentially weight this as a 20-year present value of all generation and capacity costs, and whereas the cost of investment are going to be just essentially the raw discount rate. And the two of them, if I change that, so in the temporal case, I can set delta I equal to delta O, the discount factor for operations equal to the investment, except for the last year where I maybe weigh, you know, delta, the operations present value factor by a 20-year present value factor, those sorts of things. So I can keep the same objective function. We break it into investment and operations, and we adjust the delta I and the delta O based on whichever temporal setting you're using. So we have these three different solve mechanisms. I mentioned, you know, we can use the same model in myopic. We adjust that delta operations by the capital recovery factor, reflect 20 years of operations. And then we can aggregate the delta operations over skipped years. And I can talk about that more if anybody's really interested. But it becomes an important part when you're trying to understand how we're doing these different temporal settings in ReEDS. Now, I'm going to mention model indices really quick. I'm doing this very crudely, but I express these, let's say I express these generation and capacity variables as G, and the indices on that are I, V, R, H, G, and capital as K, and that will be I, V, R, T. So these, you'll get used to, when you're developing ReEDS, you'll get used to just this very quick I, V, R, T combination. And what I represent is that technology. So we have over 200 technologies in ReEDS. Gassy Cs, gassy Ts, cold scrubbed, you know, we have 10 different wind classes. Vintage is something I'm going to talk about briefly in the next couple of slides, but it's mainly that we have initial and new capacity, and depending on the specification by the user, we can scale that up or down. R is region, and an important note here is it covers both those balancing areas and the resource supply regions that we mentioned on that map earlier, meaning R is containing every single region either at the BA level or at the resource supply region. Time slice, for now we have 17 time slices. I'm working on a project that's going to add or, you know, shrink that down a bit. And then finally T, I mentioned time here, but it should be year. And so if I think about this, I have my generation, which is indexed by technology, by vintage, by region, by time slice, and by year. And my capacity doesn't necessarily need to represent the H time slice, and so it's just IVRT. When you're developing this, you'll start to just get used to IVRT, and it's important. You'll see it a lot of places within the model. It's just important to remember what that represents. And so a general note is that the capacity variable can be at the BA or resource supply level, but generation is always at the BA level. We'll talk about that more in just a little bit. Within the model, we use what I call conditional sets, and these are the ones that are very important to know. What these do, I can provide some examples for this at the bottom, but what these do is essentially provide a check on which regions you're modeling, which time periods you're modeling, which capacity combinations you're modeling, those sorts of things. But it's very important to know a few of these. So RFees R is the feasible or modeled balancing areas. Now I put an emphasis on balancing areas because the next one, RFees cap, is the feasible or modeled capacity regions. So I can hold constraints by changing these different conditional sets. I can essentially change the dimensions of the model. So I could say, for example, on T model T, these are the modeled years in the current path to solver. But I could say either T model T is populated for 2010 only, or 2010 to 2050, and the model is going to pick up this logic and run whichever case you throw at it, or whichever set of these dimensions that you throw at it. Now we have these three different conditionals that I call the valid combinations. They're valid. Val cap is a valid IVRT capacity combination. Val gen is a valid IVRT generation combination. And then val inv IVRT is a valid IVRT investment combination. Now what this does is I may say val cap is populated for wind of new one in P1 at 2010. And it says to the model, hey, you can use this capacity variable for this IVRT combination. I've put some very simple examples here in the next bullet points. So these are used heavily throughout the model. You'll get very used to them after doing a bit of work on the model. But for the most part, these are used throughout the entire repo via these dollar conditions and GAMS. So GAMS uses these dollar conditions to say only include, if it's on the left-hand side of an operation, it's going to say only do this operation over these RHT combinations if these are true. And so our equation load constraint, the first equation in the C supply model file, is going to say, hey, populate this equation load con if if that's a feasible region that we're modeling, and if you're modeling this time period. So only populate this constraint if these are true. Now, what's happening later is, let's say I'm running let's say I'm running the myopic case. R fees R is going to stay the same. That gets processed in input. But what's going to happen with T model T is it's going to say T model T for 2010, populate that, okay? T model T for 2012, populate that and run the scenarios. T model T for 2014, populate that and then run the scenarios. So it's a way to very quickly shrink or expand your model just by changing a few sets. So I can express these general constraints and general conditions, but then later post-process that, or not necessarily post-process, but I can modify these conditions to shrink or expand the model. In the same way, we sum over certain variables. So here I'm summing, in GAMS, I'll sum over the technology, the vintage, and the region indices only if it's a val-cap combination. So here I'm using capacity. So sum over all these different indices only if val-cap is included here. And there's a lot of power to this, so I can express every single variable as cap IVRT, but there's all sorts of caveats towards it too. So why do we use these? Well, it's very useful to express one variable with all indices, but if I were to expand these out, so we have 250 technologies, we have 30 different vintages. In the very base case, we have about 30. We can easily go up to 100, 200 if we're starting to run unit level representation. Regions, we have 134 plus 356 in the US version. So we have 134 balancing areas, 356 supply regions, and that's going to get us 490 total different regions to model. And then finally, we have years. We could either go 15 to 40 different years. Now, if I take all the permutations of either the lower end of that for just the capacity variable, so if I take I times V times R times T, I easily have 55 million variables. If I add on, if I'm looking at the generation set, I have 17 time slices. I can get up to 1 billion variables very quick, whereas I don't necessarily care about combinations of I, V, R, T that I don't necessarily want to model. Maybe there's a geothermal plant that doesn't exist. There's no initial capacity for geothermal in certain regions, and so I don't want to even consider that an equation. Now, what these sorts of conditions do is it restricts the model from considering these sorts of combinations such that we can shrink down the model size really quickly just by changing these conditional sets. So if I think about the unit resolution, I can easily get up to 5 billion variables. I've had way more than that before. And the point of these is just to get all the combinations of indices that we care about. I'm going to go through this really quickly, but the modeling the capacity, so this is a capacity expansion model, and when we're modeling the capacity that's seen in the model, these dimensions can either be unit level, so I can take all of the existing capacity as of 2010 and treat that at the unit level, so represent every single unit in the United States, or I can aggregate each region's technology combination to just a single, gas CC plant, for example, or I'd represent every single gas CC plant within a region. All of these are user specified. So first, the historical binning algorithm, see this write_hintage.r script. What it does is it does a k-means clustering, and it processes the unit information into these clustered bins based on their heat rates. And then for future binning specification, see this inputs user input ict.csv file. And what this is going to do, I can show this later if anybody's really interested, but it provides a combination of technologies and years over which you're going to aggregate a representative plant. And I'll talk about that in 1 second. So this write_hintage.r script, what that is doing, I have a plot here of different technologies, and the x-axis represents what was the Ventex heat rate, but which now could be the EIA NEMS heat rate. But what this represents is the original heat rate coming from the raw data file. And what these ReEDS 2.0 heat rates are, those are the post-processed or aggregated or clustered set of heat rates for each of these units. So each one of these dots represents a unit, and I can see then that the Ventex heat rate, let's say for a natural gas CT plant, was around 10 for these guys. Well, in ReEDS, I might say, well, I have this certain cluster of these guys. They're reasonably similar, and so I'm going to put them all into one group. And then for the same set, we could think of higher heat rate plants. Maybe they're up here, and well, I might put them somewhere around 13, but all of these become one single group within ReEDS. Now, the lines here represent Area 1 and Area 2. We do this on a regional level. These colors represent Area 1 or Area 2, and we get pretty darn close to matching data, and we can actually take all of these and put them into unit level, and that's just an option in that Cases.csv file. For new capacity groupings, this is a little bit more. So the reason why we did this binning was when I first put together the model, I ran it with unit level, and I gave it every single technology would get a unique plant every year. And that just blew up the model. We can still do that, but that just blew up the model to being way, it was computationally tractable for things that we necessarily, we don't need specific technologies for every year if those technologies aren't changing much across years. So what we did, Kelly and I came up with this idea that we would have a representative plant that you could invest in from a certain period of time. So for new technologies, old technologies are essentially been by their heat rates. For new technologies, we assign them years over which we'll get a representative plant. And so, for example, I might have a plant that I can invest in. Here's a gas CC plant, and it has a specific vintage of new 3, and I can build that plant from 2020 to 2022. Then in 2023, this new shiny new model comes out. We'll call it vintage new 4, and that's going to be the representative plant that I can invest in from 2023 to 2030. Again, I'm emphasizing that all of this is scalable by specific technologies. So maybe I want a onshore wind plant for every single year that I'm going to model, a new one, a brand new one for every single year, and I have explicit representation of the vintages for that wind plant. And maybe I want to change that so I can go into this file, the ict.csv file, and change for each technology which the unit or the vintage resolution for that technology. So I'm going to move on to the actual code here. On the rest of the slide deck, I could talk more. If anybody's interested or you want to talk about the actual constraints that are occurring in ReEDS, reach out. But for now, this is more of a training session on how to use ReEDS. And so I'm basically going to go through each of these different files in turn, just to give you an idea of what they look like. I'm not going to go through every line of the code. That would take hours. But I'm mainly going to go through how this code looks and the process of running the model and processing cases and thinking about what's happening behind the scenes in all of these different scripts. So when I run this, we start off with Runbatch.py. And what this does, we discussed this a bit, but what this does is it's going to take the cases that I've specified in Cases.csv. So here if I say, okay, for those of you that are not familiar, what I'm looking at now is Visual Studio Code. And what this does is I cloned a fresh copy of the open access ReEDS repo, and I open that folder here. Here is the code that I'm looking at in each of these files at these tabs at the top. And then down at the bottom, I have my terminal, but this would be a command prompt in Windows. All of the operations that I typically do with ReEDS are all within the command prompt or the terminal. So here, I might open, if I just open Cases.csv, I can look at this, and now what I have in front of me is these are all the different options that I can pass to ReEDS. So there's 89 different options that specify different cases. For example, maybe in the time type, this is just our very basic Cases.csv file, and I have sequential, intertemporal, and window solves. For intertemporal and window solves, be sure to change your GAMS directory. So I'll pass in an argument for the GAMS directory for some of these R scripts so that they know where the GDX to R utilities are located. There's a bunch of different other options. These are explained very well in the README file. Every single option is listed out with all the default options and the possible combinations. Some good examples are I could change the costs of different technologies by changing these sorts of things. So I have ATB 2019 mid-battery costs. Maybe I just want to change that to low. And if I want to change that, I could change that just for a specific scenario here and say battery ATB 2019 low cost. And then for this scenario, my ref win scenario, the names are up here. I would then be using this different option as opposed to the default that are listed in this, this column here. Another good example is maybe I just want to end the model sooner. So in this case, I want to run maybe my sequential case just to 2020. So this will supersede the years expressed in the modeled years CSV file. But for the most part, if I want to change my end year, I can specify it in this option. And this is going to be specific to this case, whereas these are the default values, which if not replaced here, will be used. And then there's all sorts of different, when it starts on about line 44, what these are starting to do are actual, they're not necessarily input calculations, they're how we want to represent different things in the model. So for examples, AB 32 is a pollution control policy in California, and what I can do then, I can turn on or off AB 32 by changing this AB 32 switch. So this is just a Boolean. Maybe for this reference sequential case, I want to turn off AB 32 for some reason. All of these different options here are ways for us to communicate with the model via this CSV file. So I can change things for these specific cases indicated by each column, either use the default or, overwrite that default with some other option. So what Runbatch.py is going to do.
So Max, before you go over to Runbatch.py, would you mind opening up the standard scenarios cases file as an example of pre-populated scenarios if there's certain ones you want to look at?
Yes, good call. So here is that cases.csv file, and we're running. Oh, how many are we running? This is 42 different scenarios, and all of these are represented in the standard scenarios report. Very well-known set of analyses that just look at, it essentially takes ReEDS and runs it for a huge set of permutations of different cases, such as, for example, maybe I want to extend the production tax credit and the investment tax credit related to wind and solar, respectively. Well, I have that case specified here. I can change these different options, and it allows me to produce those cases. This is a very good place to start if you're interested in, looking at perhaps I want the high natural gas price case, the low demand case, the high demand case. These are good templates to use if you want to run a set of, standard scenarios for the ReEDS model. This is a good representation of the different sorts of options you can have for the model. So when I'm running this, I'll open up Createmodel.gms really quick. So this is all Createmodel.gms is, and this is what the first call is going to be. It's essentially appending all of these different files together, concatenating, A write data, B input, C supply model, C supply objective, and D solve prep. And why I do this, I can show you in the call file, but mainly we want to be able to pass all of these arguments. So here, some of these are produced, but we can see then, for example, what's a good one? Well, we were looking at the time type option, and all of these are passed into Createmodel.gms to give us that restart file, but these are just via Python, that Runbatch.py file. This is that Python Runbatch.py file is going to create this shell file. In this case, I'm on my Mac, and so it's going to create this shell file, and it's going to parse those arguments that are in cases.csv and pass that to Createmodel.gms. And all Createmodel.gms is going to do is, I'm going to run these 5 files all in tandem, and I want to pass in these global arguments, pass in these options from cases.csv as global arguments to Createmodel.gms to produce a set of inputs and model structure that is specific to the case that I want to run. So after this, I just save this. XS is a compressed solved option for GAMS, but I call GAMS, Createmodel.gms, and then I want to compress save this. This is going to give me my G00 file or my GAMS restart file from which I can start making other calls. So for example, here, right after this, check to see if that file exists. And if it does, solve 1 year. This is, in this case, I'm running the sequential case. Restart from that file I just made and save this case as A1 underscore, I called the case A1 refsec 2010. Okay? After that, so we do these options, we solve 1 year, Then we check to see if that solve was correct by checking to see if that G00 file was created. We call ReFlow, or the capacity credit and curtailment scripts, and what these are going to do is they're going to produce a curtailment output in the GDX format, so the GAMS data exchange format, and then the capacity credit values in the GAMS data exchange format. After that, so I solve 2010. Well, let's go from the beginning. I create my model by specifying all these different global options that are passed to the create model step. I call desolve 1 year. I save that as a restart file. I do these outside of the model calculations in dcall ReFlow. These are the capacity credit and curtailment calculations. And then I'll solve 2012. When I'm solving 2012, I'm going to restart from that 2010 restart file. So here, I save this as 2010. When I'm solving 2012, I'm going to restart from that 2010 solve and then save it as my 2012 solve. And in that way, I just keep layering on code, keep issuing these solve commands, and I can just keep restarting from these from the previous year. Now, in the intertemporal case, it's a bit different, but we can cover that eventually. The main thing to note here is that Python Runbatch.py, which I'll show you how to run that, will create both this directory that I can look at. Oh, it's on my other window. So what Runbatch.py will do is it will create this directory. Go GitHub, ReEDS, and runs. So here I'm in my ReEDS open access repo. In the runs folder, it's going to create this, copy over all the necessary files that are used here, and then it's going to, in my inputs case, it's going to put everything I need, but otherwise it's going to produce this shell file or batch file, which will contain all those commands that we've been looking at, and then it's going to call these. It's going to put this call, it's essentially going to say, hey, run this file, but it's going to put that command in a queue, and it'll wait. Maybe I say I want to run 3 cases simultaneously. Well, 3 cases will be queued up, and then when one finishes, the next one gets in line and starts its operations. But for the most part, what you need to know is that it'll create this runs directory, and then in that runs directory, it's going to create a case folder, depending on what you name it, and then it's going to copy over all those files, and then it'll run this shell or batch file. When I'm looking at these different files, I can get an idea for what's being created. So in this, I'm looking at awritedata.gms right now, which is the first file called in Createmodel.gms. And what this is doing, it's copying over specific files that might be needed. And then it's going to say, okay, R script, meaning this is how I call commands from R, or how I would load a script from R, call a script from R. Take this file, fuelcostprep.r, using these options that are passed in from that cases.csv file that were parsed by runbatch.py, and call this using these different options. So prepare your fuel cost prep based on these different natural gas scenarios, the uranium scenarios, your coal scenarios, all these different options. Another good one is the exogenous capacity for wind is a Python script, and it's going to take whichever GDX file you're using. So for unit data, it'll grab these different files and write those, write the appropriate data for whatever scenario you want to run. And all of these are doing essentially the same thing. A lot of these have been converted over to Python now. There's just a few remaining in the 2020 version. But for the most part, awritedata.gams will give me the ability to create all the data in that inputs case folder that will be used in the creation of the model. So when it's loading these things in, I can look at the inputs, and I'm not going to go through this. This is hands down, I think 3,000 lines of code. I'm not going to go through everything. But what this does is, the first thing it does, sets up some global options. But then I take those switches. So I mentioned the GSW switches in that cases.csv file. And those are the ones that are loaded directly into GAMS and converted over to scalars. So when I pass that global argument via the command prompt or the terminal, I can then use these percentage signs to load this in. And what GAMS will do is it'll interpret it literally. So I could say if G switch AV32 from cases.csv was 0, GAMS is going to see this as just a 0. that sort of thing. So now I can convert these global options to local options that can be used within that restart file. See supply model, right up front, I like to keep things a bit organized in these sorts of files. And right up front, we define positive variables. We have several different variables here, not as nearly as many as the older version of ReEDS, but we allow for, I think it's somewhere around 25 different variables in the model. But we have things like load by region, time slice, and time, electric vehicle load by region, time slice, and time. We have things capacity, IVRT, that same combination that I had before, investment IVRT, these sorts of things are all defined right up front. And then I define my equations. I have, reasonable explanations of what these equations are supposed to represent. But what I can do in GAMS then is in the inputs, I'll define R fees and R, and T model T can get updated, but I'll just define some simple equation where I say equation load constraint by region, time source, and time. If this is a modeled region, if this is a modeled region, and if this is a modeled time period, I'm just going to say my load is equal to some exogenous amount plus Canadian exports plus my electric vehicle load if that switch electric vehicle is enabled. Now that switch electric vehicle, or switch EV here, that is going to be processed as a scalar in GAMS from that global argument that I passed from Cases.csv. So I could set this equal to 1 or 0 depending on whichever sort of switch I want. Now I can look at my equation electric vehicle load constraint, which is indexed by region, season, and time period. Again, we have this R fees R, T model T, and then we add on this switch EV, which will allow me to specify a Boolean operator that says either 0 or 1. Do I want to include the representation of electric vehicles in my model, or do I not? And then I just say, well, the sum over these sorts of things, the sum of EV load over season or over time slices in a season are equal to whatever that exogenous parameter that I specified on. I'm not going to go through too many of these, but the main thing here is that I have val cap. Anytime I use capacity, anytime I have the capacity variable represented, I always use val cap. Anytime I have generation represented, I always use val gen. In any of these equations, if I have the T index, you should be sure to include T model T. And then all of these other things are based on whether, retire year is a scalar that we load in. Retire text depend on the scenario. Init V is just the initial classes. But for the main portion, you should always, I'll emphasize this one more time, if you're using the capacity variable, you should always use val cap. If you're using the investment variable, you're always using val int. And if you're using the generation variable, you're always using val gen. And what these do is it allows you to specify this general variable, but shrink it down to only the dimensions that I care about. But I'm not going to go through this entire file.
Just time check here. We're looking to go on a break in the next 10 minutes or so and then shift things over to Stuart. So just heads up,
awesome.
There's roughly 10 minutes left.
Cool. And to note, I've done trainings that have lasted easily 5 hours, so this is a very condensed version of the ReEDS training, but it's a good introduction to the sort of things you need to consider when you're actually running the model. And then finally, we have C supply objective. Now, I mentioned before, I emphasized that objective function calculation, the very general version of that in the slideshow, and we have then, so we have PVF capital, or the present value factor for capital. That's my delta I that I emphasized before. So this first chunk of the objective function, there's the beginning of operational cost. This first chunk right here is representing all of my, investment decisions. So I have here investment times the financial multiplier times the cost capacity, plus, the investment in resource supply curve technologies times their cost times some multiplier. All of these sorts of things are things that represent an investment decision in one way or another. So investment in transmission, investment in substations, investment in transmission times DC ties, these sorts of things are all representing investment. Whereas if I move over to the operational component, I have my present value factor for O&M, my delta O from the previous slides, times the cost of EOM times generation, plus FOM times capacity, times operating reserve costs. All of these sorts of terms in the objective function that relate to what am I doing on an annual basis as opposed to I'm sinking costs into some investment. So the operations versus investment are an important distinction between how the model sees these costs and the objective function towards which we're trying to minimize. And then finally, dsolve prep is just a very simple, it's not simple, but it goes through creating the parameters necessary for solving the case. And then you'll see some of these chunks of code that are, if the time type is equal to sequential case, do these operations. Okay, set up the PVF capital and set up the present value factor for an O&M. If you're in the intertemporal case, perhaps you want to load in some reference values of capacity, credit, and curtailment. Do the other calculations, populate T model T, all these sorts of things that are just preparing the information to be passed over to the solve routines. Now, I'll cover dsolve 1 year. All I'm doing here, so I mentioned before, we have this call file that's created by Runbatch.py. The first set creates this restart file from Createmodel.gms, which is those 5 files that process all the input information and create the GAMS model. Then I have dsolve 1 year, which is just going to solve a single year in time. So what this does is I'll pass in an argument that says I want to load whichever the current year I'm modeling is, load in all of that information, and then finally I can find here, there's a T model T. At the very end of this, I'm going to say don't model any other years, so remove any sort of assignments that have been made to T model T. If it's the current year, yes, populate that, populate T model T just for the current year, and then solve this case, and then we're going to fix some variables. In dsolve all years, I have T model T already populated from dsolve prep. So I don't need to change any of these sorts of things. I'm not going to go through this file. It's a bit ugly. I've tried to leave notes everywhere it's possible. But for the main part, if I want to run this model, let's say I have Python set up, some quick checks to see if you have at least the bare minimum are to just check to see if you can call Python, and check to see if you can call RScript, and then check to see if you can call GAMS. So 3 things there, Python, RScript, and GAMS. Now, if I want to actually run this model, I can Python runbatch.py, and you're going to be asked a few things right when you do this. The first is, so we have our fancy logo, and then I'm going to specify the batch prefix. Now, what this does is, if you notice here, everything in this file is named A1_refsec, okay? Now, what I've done here in this command prompt down, or in the terminal down here, I could say A2, and then my case is going to be called A2_refsec, okay? Or I could put in 0, and it's going to populate it with the B2020, 0714 _ time. So populating this with 0 gives you the ability to specify a batch name. So this is going to be prepended to every single file, or every single case name, etc., throughout the model creation steps. So I'll specify 0 here. I created a cases. Here, I'll show you. Open cases. So all I did here was I specified 2 different cases. Here's refsec and refend. And the only thing I've changed in this relative to Cases.csv is just this end year. So I'm going to run these 2 cases, refsec and refend, with 2016 as my end year. And what's going to happen, okay? And I'm going to say, okay, I'm going to run these cases. It says, hey, you have 2 cases being run. What's the number of simultaneous runs you want to use? And this is going to say, I want to start 2 cases at once, or 10 cases at once. It's the number of lines that are in your queue to which cases can be entered. So here I'm going to say I want to run 2 cases. The next prompt is saying, what are the number of simultaneous CC or CURT runs? If you remember from this presentation, here, I'm doing these operations in parallel. So these are the capacity, credit, and curtailment scripts. And within this parallel queue, or this threaded queue, I want to enter, in the temporal case, I'm also going to do some, I don't know what you want to call it, a sub-parallelization of these capacity, credit, and curtailment scripts. And this prompt is asking you, hey, how many of those simultaneous capacity, credit, and curtailment scripts do you want to run? Here I'll put 3. All of this really depends on the computing power that you have available to you. And then how many iterations between the model and CC scripts? Well, that's going to tell me how many times do I want to do this loop. I typically do 5. There's been cases where I've needed 8. There's been cases where I've needed 3. For the most part, I'll just start with 5. And what this is going to do then, it runs everything after this. And these are doing the financial parameter calculations that are all done in Python. It spits those out, and I disabled the actual call to this case. You'll see in a second, but boop. So it'll say it's finished, but it's not necessarily. But what I have now, so what that Runbatch.py script did is it created this directory, it copied over all my necessary files, and then it creates this shell script that has all the commands needed to run this case. Now, people have asked me, why didn't you just issue these commands via Python? And the only thing, I had originally done that, and then we wanted a way to recreate every command that's being issued, and you could either write those commands as they're being called to some file, or you could just create the file and run that file. So we just decided, let's keep a log of all the commands that we're issuing and put it in this file. Now, when this is finally done, so let's say I ran this last night. I ran A1 refsec, my 2016 case. What I'm going to look for, okay, inputs case has all my inputs. There's list files that for GAMS are essentially a log of all the instructions that were issued to GAMS. And then I have my outputs file. And in here, I'm going to have all sorts of different outputs. They're listed in that e-report file. But I'll also have this the ReEDS report, which is just an HTML file. I can open it up. And it's going to have a set of default outputs and plots that are used in, that takes a little while. There we go. So here, for example, I just ran a 2016, so I have my 2010, 2012, 2014, 2016 generation stacks. I have my capacity stacks. But as long as your Python installation is set up, this is automatically produced, and there's an Excel file for all the information that's contained in that report. The last thing I'll mention, I know we're very much butting up against time, is the output that would be made to the terminal. Well, the output that would be made to the terminal, or the output that's produced to the outputs that produce the command prompt, are all stored in this gamslog.txt file. And when I have an error, Wesley's going to cover some of the debugging steps, but this gives me a log of every command that's been issued to GAMS and the completion related to that. And so here I have my model solves, I have my calls to REFlow, all those sorts of things. All of the, at least not all the data, but all the steps are documented in this gamslog.txt file. The last thing I'll mention is that when I'm running on a Mac or a Linux machine, nothing is produced to the screen. So all of this stuff was running in the background, and there's a couple different reasons for that, but mainly I don't want a bunch of terminals opening up. But on a Windows machine, got logged out. Let me log in real quick. On a Windows machine, if I ran this case, let's say I do yeah, I have a demo here. So I'll do Python runbatch.py. I specify, the case I want to run, Wesley Cole, and then I specify my case suffix, whatever I've named my cases file. I'm running 2 cases here. It's going to start those calculations. This will take a second, but then what it's going to do is it's going to produce 2 new command prompts that are started, and Python is going to issue the commands to create those command prompts, issue the command to run that batch file within those command prompts, and they're going to run. And you'll see in just 1 second, we're waiting for the financial parameter calculations to finish. But what's going to happen is 2 command prompts are going to come up on the screen, and all of the commands for each case are going to be issued to those command prompts. I know everybody's really excited to see these command prompts pop up. But I'm happy to answer any questions. This was a lot, and it's not, in some ways, there's a lot more things we could cover. Let's see if it's up yet. Oh, it's going to take a second. I know I'm right on time now for the break, and I don't mind waiting a few minutes if anybody has direct questions. I haven't been looking at the chat this whole time, so if there are questions, I'm going to start looking at them.
Okay, well, thanks, Max.
Yeah, you're very welcome.
So if you want, you just leave this window up for a minute while we take. So we're going to break for 5 minutes. So in 5 minutes, 5 after, we'll have Stuart take over. So Max, if you want, I can leave your screen share here for a couple minutes until, and then I'll make Stuart presenter in a couple minutes. But everybody, feel free to head on break. Be back in 5 minutes, and we'll go from there.
Am I still voice?
You're still shared.
Okay, good. I think the reason why this is taking much longer is just because the other one I was only modeling 4 years, whereas these I'm either modeling out to 2050 or just to 2030, but it takes a bit longer. Let's start looking at questions. Yeah. Okay. There we go. So these are the command prompts that are created when you call Python Runbatch.py on a Windows screen or on a Windows machine, on a Linux or a Mac machine. These commands will be issued in the background. I'm going to stop sharing video, and I'm going to start answering questions if there are any in the chat.
Okay, I'm going to switch Stuart over to presenter.
Thank you. Oh, no chat questions. I guess that was just super thorough. Thanks, everyone.
Wesley, can you see my screen?
Not yet.
Yeah, let me try again. There we go.
I've got it.
Yeah.
Okay, Stuart, I've got that we're at time, so you could go ahead and take it away here.
Sure. Thanks, Wesley. So yeah, for the next, the plan is around 30 minutes or so. My goal here is to kind of just give everyone a whirlwind tour of what the inputs look like. I know there are several users who have cloned the repository really only for the inputs, and there's quite a lot there. And so, it could be really just some parts of it could just be useful data to play around with and use in other models or analyses. And it's also important when looking at the inputs to understand, it's helpful to understand some of the different switch options and toggles that you can use in the model itself, in the ReEDS model, to understand sort of ways that you could create your own scenarios and manipulate things. So as a prelude to that, Max showed an example of the Cases.csv file that essentially lists all of the different switch options. And as I go through, I'll point out a couple of these and how they relate to the input files. So if you want, you can think about doing things like saying, oh, what if I want an alternate electricity demand scenario with higher or lower demand? Or what if I want an alternate PV cost scenario, and show you kind of how to really quickly do that. So there's this window over here is just a cloned repository of the open access model. And at a couple points, I'll click over to here to this window, which is actually a run folder for our 2019 standard scenarios mid case. Because one of the things to understand about the inputs is that the inputs folder in the repository, it doesn't look like what's in the inputs case folder. And so one of the things that happens when you kick off a run is that the model copies and also processes files within this inputs folder, and the processing is done by scripts in this input processing folder, these Python scripts as well as these R scripts. And the end result is that the output are all of the CSV and GDX files in the inputs case folder. And so in some cases, this is a direct copy, but there are some cases where you have files in this inputs case folder that do not appear in the inputs folder because they are an output of some of those scripts. And so I'll point out a few of the more either useful, interesting, or complicated instances of that as I go through here. So I'm kind of just going to take it from the top and try to spend more time on the things that are more important. First off is this Canada imports file folder just contains exogenously specified data on electricity imports and exports across the Canadian boundary. And this is only used actually when you're running in US only mode, which is the default. But if you were to turn on the kind of North America mode, which would require some additional data for you to probably self-define, these would not be used. But if you're looking for, what does ReEDS assume for Canadian imports, when you just download and hit go, this is where to look. Capacity data has a lot of stuff. And so some of these files, some of this processing is admittedly a little bit messy due to some kind of legacy construction of the earlier versions of the model before Max and Kelly and Dave did the big rewrite. But this folder contains a lot of just information on different types of technologies, as well as the underlying unit database that we use to define the existing fleet. And so some things that are interesting in here, like if you want to know when ReEDS can build a new technology, or change what that first year is in which you can build a new technology, you can go into here and really easily manipulate that. So technology set and then just a year. There's some other things like this is effectively plant lifetimes if not otherwise specified by a prescribed retirement, if you want to manipulate those. And here's some other things as well. One of the really key files here is the generator database. And so you might never want to run the ReEDS model, but be interested in this information. So this is based off EIA NEMS data that we've appended things like the ReEDS balancing area, the technology specification for the ReEDS model, but there's still a lot of useful information in here. Capacity. This is a ReEDS resource region. There's online date information. And so this is, there's fixed O&M costs, variable O&M costs. So this file in and of itself could be fairly useful to explore. The headings in here are, not necessarily the most straightforward, and we can kind of help with some of that. I mean, there is well, I guess this doesn't really have much, but so if you're looking at this and not sure what things are, feel free to ask. But one way, if you are comfortable looking in the code to understand more about what's in this file, is to actually see how it's processed. And so these capacity data files undergo some of that pre-processing using two different scripts. The write hintage script and the write capdat script. And so Max did a really good job of explaining all of the ways in which we bin capacity. We take the existing fleet and bin it based on heat rate, and that's done by this write hintage script. And so if you're ever wanting to go in there, you could go into this script and sort of see how that all works. Just as a sort of general convention that we use, at least in most cases, for our R scripts, if you ever wanted to play with an R script that processes inputs independently, we typically have kind of a header section that allows you to kind of uncomment these argument definitions to manually put in whatever you want, so that you could test sort of things manually in the R script itself. By default, these argument specifications are taken through the command line that's written by the Runbatch.py. But this allows you, if you have to do any debugging or if you want to just play with it, your own input specifications, you could do that here. And so you have the write hintage script, which really just produces that bin file that called, or a bin file called hintage data. And I've got that pulled up right here. So this is an example of a file that does not exist in the GitHub repository because it's created based on how many bins you say that you want. And this has kind of the slimmed down version of the database bin at those levels for the data that ReEDS actually needs: the capacity, the heat rate, fixed operating costs, variable operating costs. And so if you want to understand the translation between the raw data and these bin parameters and what gets used, you would go into this write hintage script. And then the write cap data does a few things. It really just exists to kind of translate a lot of these files into something that's useful and more manageable given the conventions that we use in the new version of the model. And so, for instance, the prescribed builds and retirements are, the format of these is a bit legacy, and so one of the purposes of this write cap data is to sort of translate these into the the sets and set definitions and conventions that are used in the newer versions of the model. And it also kind of processes some of these other GDX files as well. So there's a lot of stuff in this capacity data folder, so that's why I want to spend a little bit of extra time on there. Going down the list, carbon constraints is if you want to apply like a national carbon cap or carbon tax, or modify the constraints from RGGI or California carbon caps. These are the files that you would use to manipulate those. Capacity factor data includes capacity factors for renewable resources at the spatial resolution of the ReEDS model itself. So the raw file here is the cfdata.gdx, which looks like this if you open it up in the GAMS IDE. And so you can see there's, like capacity factors for PV by ReEDS balancing area, ReEDS time slice, and resource class. And so you can, if you wanted to look at capacity factor data at that kind of aggregated resolution, like resource profiles, this is one way to do that. And there's also a couple other things like regional, seasonal minimum loads for hydropower in here as well. This data is also processed by our script called cfgather, but really this is just kind of like appending things together, so it's a little more organized. It's a pretty simple one. Construction schedules tells you what it sounds like. So there's different specifications for the number of years of construction and how capital is allocated over time period of those years, and that's important for financing and interest during construction. So if you want to add a new one of these, you could do that in there. Construction times, similarly, are in here saying how long it takes to build a given technology. That's implemented in the financing calculations as well. Casper specifications. So this, I'm not going to go into this folder really, but this contains all the information for the endogenous demand module. So Max pointed that out a little bit with, with an asterisk and a call for postdocs, I guess, or PhD students. And so we haven't really done a lot of working with this recently, but this has some of the information for that module if you did want to turn that on and take a look. Depreciation schedules, pretty much what it sounds like for different types of technologies. Another one worth, potentially looking at if you're interested just in raw data is, so DGen model inputs. DGen is the consumer adoption model for rooftop solar PV that we use to exogenously specify rooftop PV capacity deployment over time. And so this file contains the data for those projections for several different of the standard scenarios. So for example, this is the low natural gas price scenario. It's giving you the capacity build out, hourly capacity factors, and I guess this is probably a time slice capacity factor. So this is, if you're just looking at like what a rooftop PV projection scenario is, you could just pull these up. They are aggregated to the ReEDS balancing area, but depending on, what you're trying to do, that could still be really useful. And again, this is some, hourly 8760 data in here as well. And this is one of the, data sets that we update annually. So that always stays current, and there's lots of different options here. So if you opened up the cases file associated with standard scenarios, you'd see we pick different ones of these for different scenarios. And this is probably a good example. So if I look for the dist PV scenario switch, this is a good example where, this is it's using this switch setting. If I put something different, in a run column, it would just use whatever this text string is to look for the folder and then use the data in that folder. And so if you wanted to create your own, somehow, scale one of these one way or the other, you could do that and just make a new folder and then just put a different text string in this row, and it would use it. Financials is another one worth, I think, digging into a little bit. So I'm going to actually open up, close that now, a couple of these files, because it is a little bit, it's a little more complex how all this stuff fits in. And frankly, I wouldn't even be able to explain it all super concisely off the top of my head. But at a high level, so ReEDS has a couple different ways of thinking about financing. It has system-wide financing assumptions, just based on what are the national assumptions around interest rate, rate of return on equity, debt equity ratio for the electric sector and for electric sector investments, and the tax rate. And these things can vary by year. So if you assume there's like a change in tax policy, or if you want to assume that, you could change what the tax rate is, which happened in the most recent administration. So you can see that transition. And if you think that change in tax rate affects things like rate of return on equity, you can manipulate these things as well. And so this gives this describes the system-wide assumptions around financing. However, as probably many people know, not all technologies are necessarily financed the same way, depending on their risk assessment or their physical lifetimes. And so we also include technology-specific financing parameters that account for deviations between how you would finance a given technology and these kind of system-wide assumptions. And so this file, this financials tech, actually has several different options that you can choose between for different scenarios. And I opened up the mid case from ATV 2019, but you can see it identifies the depreciation schedule. So that plays into one of those other folders. The evaluation period, so what is the book life? The construction schedule to choose from that other table. And then this parameter is a little bit abstract, but it essentially defines what is the deviation in the kind of financing, I'm trying to think of exactly how I should describe it, and Wesley, you could back me up if I'm wrong, but it's essentially...
Yeah, it's your delta from the financial system. So if this technology is cheaper to finance than your system financial rate, you could put a delta in here. So if you want to say this technology is 3% more expensive, you could put that in there.
Yeah, and this adjusts the financial multiplier, right?
Yes. Yep.
Yeah.
And these values all come from the annual technology baseline. So if you want more details on why they're different, you could go there to get it's a different in the debt fraction, or it's a different in the assumed interest rate, or whatever it is. You could go there to see where these values come from.
Yeah, and the reason this is necessary because ReEDS operates in this world where the objective function is a 20-year net present value. So these are a way to sort of adjust for, in some cases, even like if the technology would nominally have a longer or shorter book life. And so you can see how some parameters have adjustments and others, or some technology have adjustments and others do not. And then these files are not used directly in ReEDS. They're processed by this calc financial inputs Python file, which uses a lot of the functions defined in the support functions file. And so if you ever really wanted to dig into how that all fits together, these are where you would look. And then, ultimately it's spitting out. I'm trying to find which ones. I should have opened this up ahead of time. But ultimately it's spitting out like the financial multipliers that are used in the model to adjust between overnight costs and installed costs. So there's a lot there, and yeah, as Wesley pointed out, the basis of that information is ATB, and so that would be a good where to look if you really want all of the gory details of that. Fuel prices, these are input parameters to define, coal, natural gas prices. So we use supply curves for natural gas. You have several different options for how those supply curves are implemented, which is why there's a lot of ng_ files. But so there's different types of file that are used for different components of the natural gas supply curves, and then there's different scenarios that are identified by sort of the second half of the file name. So like this is an AEO 2019 low oil and gas resource scenario file, and so you'll see that there's several of those, and which of these are used in the model depends on what type of supply curve that you want to use in the model. And then there's also stuff like we have things like this file that allows you to add a new one of these things and just specify whichever dollar year that information happens to be in, so the model itself can do the conversions. Okay, and then the fuel prices are also processed by this fuel cost prep R script. Geothermal, this contains operating costs and supply curves for geothermal resources, which is important to note that puts it in a different place than the other supply curve data. And actually, I have had people ask, like, where's the geothermal supply curves? It's not in supply curve data, so I wanted to mention that. This doesn't have much. This is just hydropower FOM costs. Incentives is potentially one, that could be interesting depending on the type of analysis that you want to do. And so this is describing things like, this is defining tax credit policies and how that is implemented. So for instance, this is saying that for hydropower in the United States, across the years, what is the PTC value that's given to hydropower? How long is that PTC available to a new build? Or if it's an ITC, what is the ITC fraction? So this is what that is for offshore wind. And then because we assume that financing is different for investments that utilize tax credit, we potentially have tax equity penalties for those technologies based on the usage of that credit. And so, you could manipulate this and play with different durations, values, whether or not there's a financing penalty, and so on. And these are also utilized by the financing scripts so that it can incorporate that information into the financing multipliers. Inflation, this just has basically a dollar-year conversions that are used in the model, which can be useful if you want to, do dollar-year conversions and be consistent with what's assumed in the model itself. Load data, so the main files here are these demand underscore, and these are defining the demand growth by NERC region or census division region for each year relative to the 2010 start year. And so again, if you wanted to create your own demand scenario, you might just create another one of these files, call it something different, and then you could really easily go into this demand scenario switch and just put your file name into there. National generation is another set of inputs related to optional policy definitions. It's kind of obtusely named, but basically this is if you wanted to do like a national clean energy standard or a national renewable portfolio standard. This is saying sort of what fraction of national generation has to be from some set of technologies. And then this file is used to define sort of which technologies are able to contribute to that requirement. And so like here's a default file saying, K imports, assuming it's like hydropower, bio-geo, hydro, landfill gas, some of the ocean stuff's not really used, wind, solar, hydro. And so if you wanted to turn on a clean energy standard and allow nuclear to supply energy to that standard, you could just put a 1 here. And in fact, you could put something between 0 and 1 if you wanted to say it gets partial credit. Plant characteristics. So this file also includes a lot of the information from the annual technology baseline. This is basically the resting place for all of the cost projections, so or most anyway of the cost projections. And so you can see the files are named by the technology and the scenario. And so this is the cost projections for batteries in the ATB 2018 low-cost case. There's batteries, conventionals, CSP, geothermal, hydro, utility, PV, wind. There's like lots of different options there, and to it's an example where you can kind of play around with the switches to choose between these files in the model. And then there are several other parameters that sit in here, other plant characteristics that are used in the model, such as the costs assigned for providing operating reserves from different technologies, for example. We've got, this is another year file that says which ATB years associated with which dollar year, forced outage rates. This is heat rate adjustments, which can be kind of a calibration parameter for historical. Planned outage rates, assumed minimum load, assumed ramp rate, which is used for saying how much operating reserves a technology can provide. So there's a lot of useful information in this folder as well. And let me see, I think this one might be worth. And so those aren't used directly. They're also processed by this script, which kind of packages it. And just to go back, there's also one that sort of packages the load projections as well. Regional capital cost multipliers is saying, different regions might have different labor rates or, other underlying differences in costs. And so this is just a file to adjust capital costs by region for, for a given technology. This regions folder has our regional hierarchy. So if you're interested in kind of how different regions are pulled together, you can, and how they're related to each other, you can easily just open this up. The regions default is the one to go with. ERCOT is just a smaller one for the ERCOT region. NERIS, actually I'm not, this is empty, so I don't, probably ignore that one. But you can see how everything's mapped together. So ReEDS resource region, balancing area, RTO, census region, state, interconnect, country, and then custom region is something you could use to sort of define your own level of aggregation for, like if you wanted to define your own type of policy constraint or something for one or more regions and how they relate to each other. And so that's a good one. Just going to have a one-stop shop for the regional hierarchy. Oh, I think my internet connection is failing me. Oh, I'm going to turn off my video. Yep. There we go, way back. Sorry about that. I'm running this off of a machine that I'm remoted into. So if I lose internet, it also means that I get kicked off that machine. So we're getting fairly close. RPS, as is fairly obvious, is all of the parameters associated with renewable portfolio standards. And so these include, the percentage requirements of the overall RPS, as well as any technology-specific carve-outs. So let me find one that actually has. So here's Delaware has a solar carve-out in their RPS, for example. If there's a clean energy standard, that can be put in as well for state-specific requirements for offshore wind. This is how much of your RPS you can get from out of state, how much hydropower should be allowed to contribute, alternative compliance payment prices, so how much you have to pay to violate the RPS. So lots of different stuff in here. And then what is this one? This is saying sort of what states can, for a given state, what states can contribute to that state's RPS. And so it's another way to constrain imports so that you don't have kind of unrealistic kind of either wheeling of power or, like Iowa provides all of the RECs that are used by everyone or something. So you can constrain that. So this gives you a lot of freedom, and we do update these things with our annual releases. And so, the 2019 version is a little bit behind. We've done an update that will be in the 2020 version. But if you wanted to play around with these, you could.
So Stuart, just time check. We're about 30 minutes in here with about 25 minutes left.
Okay, I'll try to wrap this up quickly because I do want to get in some of the visualization stuff too. So supply curve data, renewable energy supply curves. That's largely showing the interconnection costs as a function of resource potential. These are kind of technology sets. Transmission information is giving like transmission distances that are assumed. Supply curves for substations for adding new transmission, and as well as prescribed builds of transmission and costs. And then a few other things that are important. I'm not going to go into value streams. Variability. So I mentioned in the capacity factor folder, we have capacity factors at ReEDS time resolution. This includes capacity factors in these pickle files, which are Python files. This actually has hourly capacity factors for wind, PV, as well as hourly load, CSP, and these are used in our variability calculations along with this other data. And so this is also kind of another useful data set just to have handy if you want to open and play around with. A couple other things. So Max mentioned that you can run whatever set of years that you want. So this is the file where you can literally just list whichever years you want to include in a solution, and then that becomes a switch setting here. So it uses this default, but you could choose something different. And then another one that's worth just pointing out is this ICT, which seems like a weird file that doesn't make sense, but this is actually saying that this is related to how you're vintaging new builds. And this actually tells you tells the model how many vintages you want to have for new construction and in what year ranges are associated with those vintages. So for instance, utility PV we're lumping together all of UPV built through 2018, but then basically every 2 years, there's a new vintage. And so that can be useful for things like if you want to track degradation, of UPV, which we do in the model. You want to have these tight vintages so that you can keep track of how the capacity degrades over time. And you can see as these numbers basically just grow over time, depending on the technology. And so there's a switch setting that tells you the maximum number of these that you can have. But the default is 17 because that's what's in this default file. So if you wanted more than that, you would need to change that switch setting as well. But as long as you're less than that, you don't need to do anything to that switch. And then, oops. Only other thing, let's see. Another one, this is also a file has $year conversion information, some regional mappings. And then I think the last thing that I'll point out for inputs are this subset table. So you might want to change the model to create a technology subset if you want to apply to a constraint specifically to that subset, or really anything if you want to kind of categorize things for one reason or another. And so you need to, if you want to do that, you need to add a column to this file, say yes for whatever technologies you want in that subset, and then you'd also need to add that subset to here. So you'd need to add to the subset set, and then put the name of it here. And once you do that, pretty simple code change, then it's available in the model. That is useful. So that's pretty much the whirlwind tour of the inputs. And then, once everything's processed, all of the inputs as they are used in the model go into this run folder. And then, as Max pointed out, you have this inputs.gdx, which might take a second to open, that shows you all of the parameters, not only from the CSV files, but also that are defined within the b_inputs GAM script. And so this is super useful for just making sure that the data you thought you were putting in the model is actually in the model as you think it should look. And so this is always worth kind of inspecting when you're playing around with inputs. Okay, so I'm a little bit over where I wanted to be on inputs. I'm just going to jump right into outputs. So here's a run folder for the standard scenarios mid case. When you run the model, basically the reporting script salad at the end, the eReport does a lot of final data processing after the run completes, and then eReport dump takes a lot of those files and just spits it out into all these CSVs. And those CSVs go into this outputs folder to be available, and it also spits out this GDX file. These CSVs are used by our Python bokeh package scripts that first of all create these standard reports that just come out with every run, but are also really powerful for exploring the results in your own way and creating your own figures and reports that could be of interest to you. So I am going to just open up, and so this is included within the ReEDS repository. And so if you go to just this bokeh pivot folder, and it's basically a graphical pivot chart creator, it opens up this thing here. And so this underlying utility is what's creating these standard reports. And so what I'm just going to do is try to quickly walk through how they would be put together on your own. And so if you wanted, you can do this for one or more runs at a time. So you can put in a folder that has a bunch of runs. and so you can see it kind of working in the background. I'm just going to pick a low RE cost and a mid-case scenario to make things quick. So you can choose which scenarios you want to process to begin with. And then once you do that, you could start by building a report. So here's sort of the standard reports. All I'd have to do is just click on that and then hit build. One of the useful things here is if you had multiple scenarios, you can select a reference to take differences from. And so here I can say, yes, I want differences. The mid-case, choose a mid-case, right, is my reference. And I can just hit build report, and it'll just do that in the background. So I can keep playing with this while that's working. You can see what that looks like at the end. If you want to create your own figures, there's not nearly enough time to go through all the different things you can do here. But just to show an example, I'll explore some of the capacity results. And so you can just choose your result. It's going to do some background manipulations of the data, and then it'll pop up all these additional widgets and options. And the first thing you can do is we have sort of preset figures that you can play around with. And so I like to look at capacity using a stacked bar chart, which is exactly what's in the standard report right here. And so it only takes a few seconds, and then it just pops out those stacked bar charts. And so then I can actually, explore around. I can look at the numbers. There's little tools here, so you can turn on wheel zoom in on stuff, reset. I can also pan zoom. So this is my report is already finished. I'll go back to that in a second. And you can just kick out the figure by saving it, and then it'll just save. If you wanted to put that together and throw it into a presentation or something. And so there's a lot of good exploring you can do right here. And what's cool is you can also do a lot of formatting too, straight in this. And so like if I wanted to make this bigger, I can just do that. And play with font sizes, what have you. A useful thing if you're going to do that is to turn off auto update and say disable, so it doesn't. Otherwise, it'll want to recreate the plot after every single thing you do. But yeah, so there's a lot of like cool manipulations you can do, and you can add your axis labels and all that, and then have your own custom plots. And once you've done that, there's a lot of ways to export the files too. I'm just going to click all files because that gives you sort of a range of outputs. And if you do that, you'll see in this bokeh pivot output folder, it creates a folder with your username, and then the one I just exported will be a view. That's a single image or figure. And now I have, within here, I've got an HTML of that. I've got the raw data, if you ever wanted to do any tabulation or side plotting. Sometimes, if you can't do the plot that you want to do in bokeh, you could just spit this out and then put it in Tableau or whatever else you like to use. And then I'm not going to get into these because we don't have much time, but these are ways to sort of recreate the plots quickly in Python by creating your own custom report, or simply by putting this string on the after this kind of generic bokeh pivot thing. And that string actually includes all the information, like where's the data, what are the formatting options, what type of chart you want. And it actually should be able to recreate it immediately without any manual effort. And so, yeah, so that's sort of how you create plots from a sort of a standard preset. But if I wanted to turn that off, or I'm just going to go to, let's go to generation instead. I can still create whatever I want just from scratch. And so I can choose, say I want like a line plot of, like say, technology generation over the, I'm going to turn this off, over time. So I've got line plot, x-axis is year, y-axis is generation, series is technology, explode by scenario, and manual update. And then now I can look at line plots of technology generation over time. So there's wind and solar going up, gases up and down, and so on. You can see how these depend on the scenario. So there's a lot of, I think that's about as far as I'll get, but there's, really just a lot of versatility and flexibility in this tool. And actually not only for ReEDS inputs, and so I didn't go through this initially, but you can actually use this tool for any long format CSV that you want. And so you could play with this with really anything in here. If it was, as long as the raw input data is in a long format CSV, which is what all of these files are. So basically, it's not pivoted out already in any way. I think that's all I really wanted to cover given the time I have. I don't know, Wesley, is there anything you recommend I touch on?
I want to show your report you generated.
Oh, yeah, there we go. Good idea. So this is the report that I generated. So it's got the same sections as this default one that came out with our mid-case standard scenarios, but now it's got both scenarios in it. And because I turned on differences, it actually includes plots of the differences between the two scenarios. So you can really easily see the low RE cost has way more solar, a bit more wind in the midterm, less coal, less gas, and it does those difference plots for every single output. So this gives you the ability to really quickly compare across scenarios, and you can do this for as many as you want. However, I would point out that if you're doing this for like dozens of scenarios, the file size of these HTMLs gets pretty large, and they actually take a very long time for browsers to open. So just something to think about.
Thanks, Stuart. And again, feel free to throw any questions you have in chat. I'm going to take over presenter here. And then I'm going to share my screen. Okay. And then, okay, so I want to talk a little bit about debugging. So, and we'll start an error here just to have something go. So I'm going to be in the inputs file in GAMS. Let's say we were going to have a new parameter just at the top of the file, and I'm defining a new parameter, and this is called test webinar. And in order to define something in GAMS, you got to have these semicolons, and I'm not going to have a semicolon, and now I'm going to start doing something else now and say test webinar equals 1. And so we should get an error in here with this. So we'll go ahead and start this. So I'm going to just do like what you've seen lots of times here. I'm going to run our scenario, and we'll just name it something here. And then I'm going to use the test suffix because it goes a lot faster. It just runs ERCOT. So it generates things a lot faster. So we'll kick that off and start it going. And so it'll start going. It's going to run the A-write data first, so that should work fine, right? We didn't change anything in A-write data. We expect the error to be in B input. So it should cruise through there without any issue, and then shouldn't fail till it gets to that A-write data. So let me go into our runs folder. Now we've got this new folder's created. It's pushed everything over. The key pieces here are this LST file, which has the pieces that are written out by GAMS. It's like a log file. A lot of the stuff that's printed to the screen gets to go here, but it's got a lot more than that. So that's one of the places we'll be looking for errors. And then the other place we'll look for errors is this GAMS log text file. So this is getting generated, and this is getting appended to as we speak here. But you could see all the different calls. So if you wanted to see what happened, if you had an error in A-write data, one of the things is failing, you could come in and see what it's actually doing. So you could come see here's, when you're in A-write data, everything's in these. With all these weird GAMS syntax that are all these global characters, it's really hard to understand what's going on. Now you can see they're now populated, and so we could see what the actual call looks like and what all the values are. So it makes it a lot simpler to debug using this GAMS log, because you can see what the values are, and you go in and say, oh, look, I told it to use this, but I actually didn't want it to use that, or I spelled it wrong or something, and it'll be easier to see what's going on. Okay, so we have our run failed. You can see the thing closed. So if I go back to my my piece here, I go to outputs. The outputs folder is empty, so nothing got created. It didn't work. Also, usually to start in the LST file, I could see that only the inputs LST was created. There's no other LST files. There should be one for every year it's solved. There's not anything here. I could open up the LST file, and the key is to search for 4 asterisks, and then that will bring you down to where the error is. So it says, oh, you've got an error down here. The error is 97. If you go to the end of the file, GAMS will tell you go to the end of the file, scroll up a little bit, and then it'll tell you what error 97 is. So it says you have explanatory text that's not starting with something it's expecting, or maybe there's a missing semicolon on a previous line, and that's what our error is. So if we were to fix that, it would run again. But that's how you could look to see, I added something's wrong, what is it? You could look in the LST files, they'll tell you. Sometimes you'll get different kinds of errors, like maybe everything was created and you're looking at your model outputs and you see that, oh shoot, in 2045, we're getting a whole bunch of, we're getting 10,000 megawatts or 10,000 gigawatts of capacity, some ridiculous answer. And that's where opening up your GAMS log and inspecting the GAMS log file can tell you what's going on. So you'll come down to reading things, and it'll say something like here it says, oh, you've got a compile error. So we were in Createmodel and there was a compilation error. We just saw that by looking at the LST file. But you could also see be looking at a GAMS log file and you get a solution that's it'll say infeasible. This model was infeasible at this point, and that's why you got the really weird answer in the output. So the combination of the GAMS log and LST files are really the core of where to go when you're debugging. So there can be errors outside of GAMS. So if it's not infeasible and it's not a compilation error like we saw here, like if we change something in the Python code or one of those R scripts and that threw an error, that's a little harder to debug. Those kind of errors won't just show up in turn, we haven't developed the stuff that says, hey, look, it was that write capdat.r file that has the error in it, so go look there. Usually for those kind of errors, if you're in the inputs and it says, I can't find this file, so it's like I'm looking for the file that was written by write capdat, but it's not there, that's a pretty good sign that there's an error in write capdat. And so then you could go back and say, well, why didn't this create the file? You could, start here with looking at the call to write capdat and saying, does my call look okay? Do or is there something wrong? So, for example, if it was a right hintage, there's a file supposed to be out of right hintage, it's not showing up. I'm going to come here to the right hintage.r and say, okay, it looks like everything I have looks okay. So now I'm going to open up right hintage, and I could give it these arguments because I know what the arguments are, and start stepping through the right hintage code to say, oh, here's where it is. There is this new thing I added. It's, I forgot to tell it the dollar year of the input file. I added a new input file, but I didn't tell what the dollar year was, and so it's trying to convert the dollar year. It can't because it doesn't know what dollar year my input is. So that kind of thing, it can be a little bit of work to find these, but the information's here to be able to diagnose. Okay, so I'm going to stop sharing there because we're at the top of the hour. I guess just summary here at the end. So we've covered a lot of material. We could spend a lot more time on this kind of stuff, but certainly if you have questions or if you have thoughts on things that we should be covering, feel free to send them over. Or if you're struggling with getting the model up and running, you're welcome to contact us just to get insights there. We are planning on posting the video that we've used here to make it available for other folks. But we're going to go ahead and close up because we're at time. So thank you all for participating. Thanks for being here. Thanks for your interest in the ReEDS model, and certainly feel free to follow up with us if you have other questions down the road.
Yeah, Wesley, real quick.
Go ahead, Stuart.
Fernando Morales asked if we're going to make this the recording available. Is that we are,
correct?
Plan is
to make the recording available. Yep.
Yeah.
Okay. Cool. Thanks, everybody.
Thanks all.
Thanks, everyone.